Hey, good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And today we are talking about the normal distribution. Yes, we are. And here are some examples that I pulled from the internet of data that is normally distributed. You'll notice a nice smooth bell curve. They call it a bell curve because it looks sort of like a bell. So what is this normal distribution thing? Let's have a look-see, shall we? Before, we have always been talking about discrete data. Discrete data really is data that can be counted, like there are 17 trees in the yard, or in this box there are 32 apples, something along that. Well, we use the binomial, the normal distribution to make sense of what is called continuous data, and we talk about a continuous random variable x because we're talking about continuous data as opposed to discrete data. Okay, we'll talk more about continuous in just a second. Okay, so we have the aid of what is called the probability density function, and we'll see that in just a second. And since the sum of all the probabilities of a particular event is equal to 1, we can say that the area under the probability density function is equal to 1. A little bit of calculus there. So from a to b, the integral of a to b of f of x, being where f of x is the probability density function, is going to be equal to 1. Okay, and so the probability that a random variable x lies in a particular interval is given by, let's say, from c to d. We just have to find the area under that curve. That would be the integral from c to d of that function. Okay. So what is this all about? Well, and what is continuous data? Continuous data is like weight or temperature because it's continuous. If something increases in weight from 25 grams to 30 grams, it hits all of the weights in between. Temperature rising or decreasing, like going from, I don't know, 25 degrees Celsius down to 15 degrees Celsius. You hit all the temperatures in between. Okay, so for a continuous variable x, the probability that x is exactly equal to a particular value is 0. What that means is it's not possible to calculate. Okay, that seems a little weird. But this example does a nice job of explaining it. If we have an egg, what's the probability that it will weigh exactly 17.9 grams? Well, the probability is 0. And why is that? Well, we can never be absolutely sure it's exactly 17.9 grams because our scales can only be so accurate. I mean, we could keep adding significant figures till the end of time here, and we would never know if it's exactly 72.9 grams. We're limited by the accuracy of our measuring devices. So for a continuous variable, the probability is always calculated on a range. It's between two values. So we can find the probability that the egg will weigh between 72.85 and 72.95 grams. Okay. Now, if the data were discrete, we could find an exact probability, but with continuous data, you cannot. Okay. How does a normal distribution arise? Well, if you think about oranges picked from a tree, there's several different factors that would affect the weight, the genetics, fertilization, sunlight, weather. And what you will find is that a lot of the fruit, most of the fruit, will have weights close to the mean of the fruit, while fewer oranges will weigh a lot more than the mean weight, and a lot less than the mean weight. And that results in what is a normal distribution, something like this. If we were to graph it, maybe even better would be something like this. You know, most of the oranges would weigh in here, and then a few of the oranges would be really light, and a few of the oranges would weigh a whole heck of a lot. And these occur in nature and other applications more often than you would think, and these being normal distributions. Physical attributes of a population, such as height, weight, and arm length, is normally distributed. Crop yields, scores for tests, that's a big one. Here's a graph on the Wechsler Intelligence Score where the mean is 100 and most of the population scores right around the mean. And in fact, for a normally distributed function, actually 68% of the population will score within one standard deviation of the mean, okay? Approximately 68%. So here, our standard deviation is 15, okay? So some will score within 15 points above and 15 points below the mean. That's 68%, 34% on each side. 13.5% will score between 1 and 2 standard deviations above the mean, and 13.5% would score between 1 and 2 standard deviations below the mean. Okay, so this is just sort of a nice example of that. Intelligence tests always come out normally distributed. This is the function of which we speak. Luckily for you, we don't have to have this memorized. It's just there. It is the function that defines the normal probability density function. We write the random variable x is distributed as a normal function with mean mu and variance sigma squared. It's called a normal curve. It's symmetrical about the vertical line x equals mu, where this is the mean. So it's exactly the same to the right of the mean as it is to the left of the mean. And as x goes to plus or minus infinity, the normal curve approaches its asymptote, the x-axis. F of x will always be greater than 0. And the probability must be 1. Therefore, if we were to integrate from negative infinity to infinity, which is a bit beyond the scope of this course, not far, you're real close to being able to do it, then that would be 1. And again, like we said, more scores are distributed toward closer to the mean, whatever the data may be. Okay? So what's the geometric significance of mu and sigma, the standard deviation? Well, if I take x equals mu here, I calculate the standard deviation, and I plot it right here. If I go straight up, this point on the the normal distribution curve will be the point of inflection. Okay, so the standard deviation is directly down, perpendicular to the x-axis from the point of inflection. On both sides. Okay, that is one standard deviation. Okay, now normally distributed, these are more exact here, and this is what we will be using, though you do not have to have this memorized. For a normal distribution with mean mu and standard deviation sigma, the percentage breakdown of where the random variable could lie is shown below. So there's a 34.13% chance that a random variable selected at random, lies within one standard deviation above the mean and the same thing below the mean, one standard deviation below the mean, and a total of 68.26% are within one standard deviation of the mean. That makes sense because anywhere from here to here is within one standard deviation from the mean, as is from here to here. Okay. Now, if we go within 2 standard deviations, that total rises to 95%. So 95% of the population will fall between or within 2 standard deviations of the mean. And you can see how it progresses on down the line. Now, make sure you understand that between 1 and 2 standard deviations is 13.59%. And between 2 and 3 standard deviations is 2.15%, and then greater than 3 standard deviations is 0.13%. It's symmetric, so the same thing goes for below. All right, enough yammering. Let's just do the one and only example just to make sure you understand these percentages here that we have been talking about. Okay, so The chest measurements of 18-year-old male footballers are normally distributed with a mean of, okay, there we go, of 95 centimeters and a standard deviation of 8 centimeters. Find the percentage of footballers with chest measurements between 87 and 103. Okay, so let's do AI. Okay, so let's see, our standard deviation is 8 and our mean is 95. Okay, so let's do 103 minus 87, and I have a sneaking suspicion that that is going to be equal to 16, which it is. Okay, well, that means that's within one standard deviation above and below, and I'm just going to use this little figure here for us. The mean is 95. Okay, plus 8 is 103, and minus 8 is 87. So we can say that approximately 68.26% of the footballers will be within, will have chest measurements between 87 and 103. What about AII? 103 and 111, II. So 111 minus 103 is 8, so that's just another standard deviation. So that's right here, 111. Well, that's between 1 and 2 standard deviations, so that would be about 13.59%. So the object here is you're just finding your way around the a normally distributed set of data. Now, this is continuous data, right? Because it's measurement, it's chest measurements will be continuous through here. B, find the probability that the chest measurement of a randomly chosen footballer is between 87 and 111. So that's from here to here. So the probability is just the sum of these two percentages. And if you take 68.26 plus 13.59, I'm saying approximate because it's not exact, we get about 81.9%. So an 81.9% probability that a randomly selected footballer will have a chest measurement between 87 and 111 centimeters. So part C. Now here comes the fun. Find the value of K such that approximately 16% of chest measurements are below K centimeters. Okay? Below K centimeters. Okay? So I know that 50% of my data is to the right of the mean and 50% of my data is to the left of my mean. So I know, and I have no idea yet because I haven't thought this through, but I know, let's just, well, here's 13.59%, so K is somewhere in here, some value of K, right? So that is going to be whatever is 16%, whatever I'm sorry, K is going to equal the value where to the left is 16% below the curve. Now it happens to be, not happens to be, it is 87 in this case. K equals 87, and I'll show you two ways that you could have come up with that. Well, 13.59, I guess they really want me to come to that meeting. 13.59 plus 2.15 plus 0.13 is approximately equal to 16%. Or you know that this is 50% right here, so 100% minus everything to the right of the mean, and then minus this 34.13% is also approximately equal to 16%. Okay? And that's less than one standard, everything beyond one standard deviation below the mean. So that's how you could come up with K equals 87. So this is where we are. Again, this is just a lesson to get you familiar with the normal distribution. We'll get into some heavy-duty stuff in the next few lessons. I am out!